I'm very glad to be here today and to be able to start the conference. And I thought the best way to start the conference is to start thinking about why what we do every morning matters. And in terms of MEMS, performance matters, but why does it matter? And I'm going to try to explain, in terms of applications, different application requires different performance KPIs. And I'm going to try to go very quick in terms of many different types of applications, but also different types of sensors. So hopefully this actually gives you an idea of the why performance matters and that it's across the board. Very quickly, I should mention about TDK. They acquired InvenSense. I work for InvenSense, but they've acquired a number of sensors companies. And really, sensors is the next pivot of TDK. You probably have heard of TDK before, and they've done the ferrite materials. Then they did a pivot for all the things like cassette. I'm sure you know the TDK cassette. Then they did another pivot, which was all about the hard drive magnetic heads. And sensors is the next pivot for TDK. And if you look at all these companies, you probably recognize a number of them. We used to be the last acquisition of TDK in sensors, but actually we just finished 2 weeks ago the acquisition of Chubb, which is a time-of-flight sensors. And if you look at all these companies, that's about $2 billion of investments from TDK. So TDK is very serious about sensors. Oh, maybe one thing I should mention on the right side is not only we do have a number of sensors, but we actually have a view on the market, and we try to address multiple verticals. And that's very important for what I'm going to describe afterwards, because for one sensor, we address multiple verticals. And therefore, the requirements for the same sensor may be very different depending on the use case and the verticals. So in terms of portfolio, it's quite wide through all these acquisitions. We have the IMUs, which is the axle and the gyro, 6-axis, you probably have heard, temperature and pressure sensors, Hall sensors, MEMS microphones, fingerprint, ultrasonic fingerprint, angle sensors, and the most recent time-of-flight. I mentioned about applications, and this presentation is really about showing you that MEMS performance is really application dependent. And all these nice hexagons is showing you a number of areas where we are already involved. And it's not even all of them. From, of course, smartphones, where we've been doing a lot, to augmented reality and virtual reality, and I'm sure that our colleague from Google will talk more about this. Automotive, industrials, robotics, audio with microphones, and of course, biometrics. So I'm going to start with the consumer motion, because this is where you have volumes. It's well known, but then we will move to other, like industrial, afterwards. So in terms of smartphone, one of the things that's becoming very important is the quality of the imaging. And you probably have heard of the name OIS, and EIS also. So a lot of these smartphones are starting to deploy not just one, but maybe two, and at some point 3 OIS will become a trend. And all of this means you need really good motion sensors to detect the motion of the hands. And why is that? It's because we still cannot keep our hands still when we take pictures or videos. Our hands keep moving. And even though it may not be big movements, it's still movements that would make the video and the pictures you took afterwards not as nice to enjoy and to relive the moment. And so having really nice compensation for this motion of your hands is really important. And you have two types of hand jitters, really. You have the rotational hand jitters as you move, but you also have the linear hand jitters as you, for example, you want to pan. And this combined means that you need to be able to have really nice OIS performance, to have really nice still images or videos. If you look at how to make this happen, you really need, on the OIS side, very low gyro noise and sensitivities, and also very good high temp stability, because the modules actually heat up very quickly. And so you need to be able to keep the performance across temperature range as the temperature increases. You also have a number of OIS which are called 4-axis. And in this case, what really matters is to have very low accelerometer noise. And the sensitivity also matters a lot. So there are first-degree impact to quality OIS. This is probably my only product slide, but it's just to give you that we really care about this, which is about the gyro sensitivity, just to give a KPI of less than 0.5%, and that enables a higher suppression ratio, but also helps to avoid dynamic calibration on the main board OIS when it's being used on main board. The gyro bias drift over temperature is very, very low, and that minimizes the temperature impact, which actually impacts the suppression ratio. And that leads to superior OIS performance. It also provides a total two-stop OIS performance advantage in real use case. And the accelerometer, of course, is really important, like we mentioned, for the 4-axis OIS. Now, I mentioned about imaging, but it's also indoor navigation, where the gyro sensitivity really matters. And here we are just showing you just very concretely what it looks like when you have better gyro sensitivity. And here this is actually a mall in Sauvage, Westfield. And we have actually looked at what would be the outcome of 0.3% versus 1% sensitivity. And what you can see is if you were the person that starts entering the mall, go to number 1 step, turn right, 90 degrees, very simple. We're not trying to do someone that keeps walking different paths. Then go number 3, and then come here. This is really where the person is, just in the corridor between the two shops, facing this shop. This is what our sensors with good performance can get you to. We can typically know you're here, very close to the real position. The maximum error is actually still in the corridor. But if you look at lower performance accelerometer and gyroscopes, then you would end up actually in the different shop than you are. So for indoor navigation, to have really good gyro sensitivity really matters. And you can see this is a very simple use case where you just turn around. Imagine as you walk longer and longer and when you don't have GPS to help you, to assist you. We talked about smartphones, but IoT is also about a number of other products. For drones, what matters is the bias, the time, and the temperature stability. When you look at AR/VR, and John Zhang, I'm sure, is going to give even more detail than that, the temperature nonlinearity, the hysteresis, noise, and temperature stability really all matters. And this is really tough because for MEMS to have really good temperature nonlinearity and very good hysteresis, very low hysteresis, is a really hard challenge to work on. For robotics, here robotics is really about the gyro because it keeps turning as it goes through the room to, in this case, to do some vacuum cleaning. Then the bias stability and the noise and the TCO really matters. Now you could think this is all motion sensor and that should all work the same, but actually, depending on the use case, you really need different performance, and therefore you may need different parts, even though it's based on the same platform technology. I have one more example, which is about AR/VR on the gyro bias. And this one is interesting because with the temperature and the constant movement of the head, you're going to have a drift that happens in the motion. And what that means is, let's assume that you're sitting on your sofa and you're watching a VR content. At some point, it's going to drift to the point where your neck is going to turn, and that's not what you want. You want it to be really without drift, so when you're seated, it doesn't matter. You're always looking in the right direction. Today, if you look at the Google Daydream controller, you have the reset button so that it can reposition depending on the drift. But you shouldn't need this button. You should be able to stay seated and always look at the right direction that you meant to look. So that's one example that's very interesting. And that's the gyro bias. And so the gyro bias, if you can make it really low, it means that you don't need to keep turning. This is a very high-level summary about what I discussed about imaging, navigation, virtual reality, and you can see what kind of hardware spec is most important for each. So for navigation, clearly it's about gyro. IoT, like the vacuum cleaner, it's also about gyro. But some of them is also about the accelerometer. Some of them is about tap robustness, for example, so that you can actually have some tap on the VR controller and still you can capture all the signals of the head movements. Now, on top of all this, there's one more use case which is interesting for smartphones, which is the vibration that's caused by the speakers. And audio is becoming really important, and they want to have as much loud sound as possible coming from the smartphone. But when you turn on the speaker, the PCB will start to vibrate. And when it vibrates, it means the motion sensor is going to pick up this vibration. And what we say, it goes crazy because this smartphone is vibrating, but it's not the movement of your hand. Or it's not the movement that was supposed to be captured. It's actually the speaker that's vibrating because it's loud. And so here, what really matters is to be able to actually be resilient to this vibration. To really be able to avoid this vibration to be picked up as movement that was never intended to be. And that can matter for whether you are recording, whether you're in indoor navigation, where the speaker will speak out loud the directions. It could be in VR, where you actually have the mobile that you have put onto the headset. It really matters. So I've talked a lot about consumer. I'll move now to the industrial. Industrial is even worse because the expectations on the requirements is even stronger. You really need high quality. I'm giving you 3 market segments that we are working on, and just to give you an idea about what matters the most in terms of performance for each. So for precision navigation, you really need much higher precision than what I was showing you in the mall. In this case, temperature, offsetability, vibration robustness. If you're on a tractor, the vibration will be even stronger than what I was presenting for the speakers. But also, you need a very low noise gyro. Very, very low noise. If you start to look at automation, then here you have very high bandwidth, very low noise requirements, and the temperature range can really go way wider than you would see in consumer. And structural assets and monitoring, again, ultra low noise. This is a table stake. Offset stability matters, and of course, you can actually use sensor fusion to actually take many more inputs together. I want to talk about, so I've talked a lot about motion. Let's move to pressure sensors. So pressure sensors can be used in an increasing number of use cases. And why is it the case? It's because actually we get to a point where the noise level of the pressure sensor gets so low, you can actually detect to the level of step counting. Or you can actually detect whether you're lifting your arm and bringing it down, like this. It gets to that point of precision. And as you get better performance and better precision, you can start to think about new use cases. Here, for example, would never have used pressure sensor if it was not for much higher precision. Indoor navigation, I will have a video to show you that's pretty cool, that shows you can actually detect you're moving from one floor to another. You have 911 in the US, and I'm sure it's going to expand to many other countries where it's great that you have the location of the person calling 911 or emergency services, but if you arrive in a building of 20 floors, it's not very helpful unless you can say, actually, it's on the 5th floor, or it's about between the 4th and the 6th floor. That will help the emergency services a lot. Driving, of course, and activity monitoring, and I have some example about activity monitoring, but also drones. So, on pressure sensors, there are a number of performance criteria you can think of. The most obvious is the absolute accuracy, the relative accuracy, also the temperature, output data rate, power. Noise start to be, like I mentioned, very interesting because as you get lower to noise, you enable new use cases. and environmentality compatibility. So let's talk about noise for a second. Here it's about relative accuracy. We're talking about being able to detect a relative increase or decrease of height. And here we really did very simple measurements here, where we went to our car park, and there are steps, and the steps are 18 centimeters high. And we simply went with two different pressure sensors, one that we've seen in the market and ours. And they are both on the laptop of the guy there, and he walks up and down the steps. In this case, he only walks down. And you can see the steps, or you can see the increase that happens. It's very noisy for the other sensors that we use as a comparison. So here it will be very hard to see which steps you've taken, up or down. But in this case, if you look at the zoom, which is the first 4 steps, you can really see a difference of 2.1 Pascal, which happens to be 18 centimeters. So you can see, just looking at this, you can detect which ones are steps up. Now, this is indoor, and here what we're trying to do is actually to combine, to fuse accelerometer with pressure sensor. And of course, we have very low accel noise requirements, but also pressure sensor is very low requirements. And as you start to take them together, you get to a point where it's extremely accurate. And here what we did is we went up the stand, we decided to stay for a while to see if there was no false positives, and then went down. And it was extremely precise. And one of the reasons is to use the accelerometer is the pressure keeps changing over time. Even in this room, the pressures will keep changing. Someone opens the door, the aircon, a number of things can change. But as you use the accelerometer as well as a pressure sensor, you can be extremely precise about what's happening. And this is an example you can't actually see. I'm not sure why. You can't see the lines, but here we are taking the input of the accelerometer and the pressure sensor together, and some algorithm compensation to get to this very precise layer counting I was showing. Drones are coming. So I was talking to Manuel. It looks like it's at 40 million drones today in the consumer market, toy and high-end consumer market. So maybe this one is a bit too ambitious, maybe for next year. But there are more use cases coming, like infrastructure maintenance, entertainment, media, agriculture. And the trend is all about improving more capabilities from these drones. And here the MEMS performance can really make a difference. And so I want to show you this video. So here I need the help of Elsa. Can we start the video for this one? So here you can see the difference between a normal pressure sensor, which is already a good low noise, on the left, and on the right, the one from our company, which is very low noise. And this is everything equal otherwise. And so if you can start one more time, you can see this drone on the left is very hard for keeping its altitude constant. And the one on the right is actually really, really nice and stable. And here we are only using pressure sensor. We're not using other sensors for this use case. I talked about indoor navigation. And so here I'm going to play the video where you can see the altitude measured by the pressure sensor as someone goes inside. And so I'm going to ask you to really look at where the person is entering into the buildings and how the altitude is nicely recorded. And you can see the sensor fusion in red and what is a GPS solution in blue. And so, of course, the blue is not on the map when it's inside the building. You don't have the information then. And in addition to being able to record the altitude, we also know what is the context. Is the person walking, running? This is really interesting to be able to capture all this information. And so here you can see going up, which also means that in terms of use case, you could have a solution that knows which floor you are in the mall, which means that it knows which shops you're close to. There's no point for you to know about a shop that's on the second floor if you're on the third floor. And that level of performance really creates new use cases. I also wanted to mention microphones because that's also MEMS. And here it's very well known, but ISNR, IOP, low power, ultra small size create new use cases. So if we talk about SNR, you all know about the example where you need to be all close together to make a conference call, and that's not really good. SNR is really good to have a quality conference call. If you think about ISPL, this is also very important so that your microphone doesn't click. And it enables really nice clear audio, whether the sound is at a normal range or it goes very high. You could think of one where you're recording a video of a friend and an ambulance comes by and suddenly all the audio is messed up. And if you have a very nice ISPL microphone, that actually will improve it. So range finding, time of flight, is really cool. If you think about everything we do for sensors is to know what's happening around us, around our device. And here it's actually about knowing the distance between our device or our robots and the world. And so it's of course very used already today for when you reverse to know if you're going to bump the wall or not. And the more precise and the power and the smaller it can be, the more you could have inside the same car. Drones and robotics already using them, but you can imagine a number of devices that can take advantage of knowing exactly the distance between them. It could even be the point where, as you approach your hand to your device will sense it and start to power up some use case. I want to mention also about fingerprint, ultrasonic fingerprint. And I don't want to talk too much about it, but just to give you an idea that we can start to be able to get very nice fingerprint scan, even on the glass or on the aluminium. So start thinking, just for aluminium, start thinking about what you could do with fingerprints in a very harsh environment where actually you don't need a glass. It's just aluminium, and yet you can have your fingerprint taken. Automotive also matters a lot. So for automotive, you have in-cabin, where biostability, biosurface temperature, sensitivity over temperature really matters. But you start to move into safety, then you have way more requirements. ISO requirements, very high range, 125 degrees temperature range, because it can get really, really hot, and you never know where the car is going to be used. It could be used in a very cold country or a very hot country. And vibration, resiliency is really important. You can imagine close to the engine or driving. Autonomous driving also is kicking in, and I'm sure there will be a number of presentations talking about this today and tomorrow, but that also drives a new level of performance requirements. So I want to conclude with these three words: MEMS performance matters. And I look forward to hearing from you, because as we see it, whether it's consumer with an increasing number of devices, whether mobile or IoT, whether it's automotive, industrial, or very high-end navigation requirements, we believe MEMS performance matters. Thank you.